Kia ora koutou. This video is for people who are away sick today in our first lesson on differential equations. So in today's class, I'm going to go through how we form DEs from word problems, but I also want to show you an example of a fully worked up applied problem. So this one here is about merit level for level 3, and it will probably feel pretty easy after a couple of days. But today, what I want you to do is just kind of watch it, follow the steps, and then see how much of it you're getting the hang of. The big new technique that I'm going to be using in here is something called separating the variables. And we're going to work with a real life situation. So this is really common that we have a whole lot of words and not much obvious maths. We're given information about radium. An isotope of radium has got a half-life of 1600 years. So after 1600 years, that means that half of it has decayed radioactively. And this is the important bit for solving the problem, is that we're told that the decay is proportional to how much radium is left. So we're going to write that as a rate of change. So the rate of change of radium with respect to time, all right, so N is the amount of radium, and T is time in years. So the rate of change is proportional to, so going a bit slower, is proportional to how much is left. And we can write how much is left as N. Now, we know that that amount is decreasing, so I can write that as negative K times N. So that's what it means for something to be proportional to something else. And this is where I'm going to start doing this new thing called separating the variables. I'm going to treat dN by dt as a fraction with a numerator and a denominator. And we've talked quite a lot in class about why it's okay to do that. So you should be feeling reasonably good about that. What I'm going to do now is get all the stuff with n's to one side. So we're going to have 1 over n dn, and I'm going to leave this negative k over here. I'm going to multiply through by dt. So I've now got the n stuff together on one side and the other stuff together with the t. If I had any terms with t, they would come over to this side. But in this case, I don't. This is a classic differential equation. You'll solve ones like this over and over in the next few months. What I'm going to do now is I'm going to integrate both sides of that equation. So the logic is that if this is always true, then the integral of each side must also always be the same. Right, let's take each side in turn. On this side, I get the natural log of n. Now I could write the natural log of n plus c, c1, and then on this side, I'm going to get negative kt plus another constant of integration, c2. But these two things are just arbitrary constants, so we can shove them together. So I'm going to write that as this, but that's about the only time I'm going to do that this year. What I'm going to do from now on is I'm just going to say, well, they all wash up together, so when I do this side, I won't bother writing down that plus c. I will just put it in on this side. So the natural log of the amount is equal to negative kt plus c. What I'm going to do now is I'm going to do e to both sides. So we get n is equal to e to the negative kt plus c. And I can write that as e to the negative kt times e to the c. And I can relabel this thing here as another constant. And I'll often use capital A for that, not always. So you can see in here that I've got what is called a general solution. This is giving me an equation for the level of the amount of radium for the first time. And we can see that it's going to look like this. When t is 0, we're going to have our initial amount, and it's going to decay. So we're going to have some kind of curve that looks like that. We don't know exactly how steep it is yet. So our job now is to figure some of that stuff out. And in this problem, we were told something important about the half-life. We were told that after 1600 years, half of it has decayed radioactively. So this first thing that we've got here is what we call a general solution to a differential equation. I'm going to go on now and use it to solve a problem, which is getting a particular solution. So the particular solution is where I've gone and figured out values for the two constants. All right, so what can I do now? Well, we know that at t equals 0, how much have we got? Well, n will equal a times e to the 0, which is just a. What about after 1600 years? Well, at t equals 1600, we know that we've got 0.5 of that initial amount left. We can use that information in here to figure out the value of K. And that's what we'll do now. So substituting that in gives me this 0.5A, right, which is the amount of radium after 1600 years, is equal to AE to the negative 1600K, right? So I'm substituting in T. Dividing both sides by A gives me 0.5 is equal to E to the power of that. And now I take logs of both sides. Lastly, I divide through by negative 1600. So I get K is equal to the natural log of 0.5 divided by negative 1600. And K works out to be 0.004332. Okay, so we're getting somewhere. We've got a particular solution. We now know that N is equal to the initial amount, A, times E to the negative 0.00, I think I've missed a 0 in there, guys, so third 0, 4332T. And that means that we can put some shape around our graph, and I've done that on the next slide using GeoGebra just to show you what's going on. Okay, so here's my radium isotope, and this is just my percentage, right? So I just made A equal to 100, and you can see that this looks about right. So when we've got, where's 50%? Well, 50% is here, and that's, oh, it's not that accurate, but you can see that that's at 1600. It's not that accurate because I didn't mark that on my scale, which was a bit silly. And what we're looking for is when are we down to 10%, right? So you can see on here that we're expecting that my answer should be, I don't know, somewhere out around here. And that's what we've got to do next, is to finish the question off. Right, so we want to figure out when is n equal to 0.1a. Substituting in, we get 0.1a is equal to a e to the negative 0.004332T. Divide through by a, 0.1 is equal to e to the negative 0.00043322T. Now I take logs of both sides. So the natural log of 0.1 is equal to negative 0.00043322T. I bet no one's watching. Are you still watching? Maybe. Okay, and now T works out to be, solving all that, 1 divided by the other gives me 5,315.08 years. Now, in context, it would be pretty stupid to have in there. That's far, far away. So T equals 5315 years. Or if you're doing this in an A-level problem, you'd probably go to 3 sig fig and you'd do 5,320 years to 3 SF. So there you go. That actually took longer than I thought. There are a lot of steps in here that you're going to get very comfortable with, but to make that happen, I'm setting heaps and heaps of practice on this topic. So just going right back to the start, can we just go through the steps that we did? The first thing we did is we did the setup, right? So we set the DE up here using these words up here about it being proportional. Then we separated the variables, and that's what this step here was, right? So that's separating the variables. Then we integrated both sides, and doing that got me down to here. So that was my integrating. And then I wanted to get what we call a general solution, where we have y equals or n equals, and that was what came in here. Then we use the specific information about the problem to work through and get a particular solution. So thanks for watching. Hope you're all feeling better soon, and I will chuck some notes onto Google Classroom as well.